take this opportunity to introduce our speaker today. So with us we have Professor Olivier de Weck from MIT. He is the Apollo Program Professor of Aeronautics and Engineering Systems at MIT. He earned his degrees in Industrial Engineering from ETH Zurich and Aerospace Systems from MIT, where he's currently the Director of the Engineering Systems Laboratory. His main research is in systems engineering with a focus on how complex technological systems, such as satellites and launch vehicles, are designed and optimized, and how they evolve over time. He's made a lot of methodological contributions by his group have included time-expanded domain decision networks, generalized multi-commodity network flows, as well as software tools such as Spacenet and HavNet. He's also a fellow of AIAA and a former chair of its Space Logistics Technical Committee. And he helped develop the first integrated model of the next generation space telescope, now the James Webb Space Telescope, and the concept of interplanetary supply chains. He previously served as editor-in-chief of the journal Systems Engineering and is a former senior vice president of technology planning and road mapping at Airbus, where he was responsible for road mapping $1 billion R&D portfolio. And his passion really is to improve life on our home planet Earth through research and education, while paving the way for humanity's future off-world settlements. So we're really lucky and excited and honored to have Ollie with us today. So please join me in welcoming Ollie.
Thank you. It's wonderful to be here. Thank you, Professor Haji, for the introduction. It's great to be here. Thank you for the invitation. This is, I think, my third visit to Cornell. It's been a while. We had a workshop on satellite constellations, free-flying satellites here maybe 5 years ago with Danny Selva was here and hosted that. So that was really wonderful. And I want to talk to you about blurring the boundary, integrating system of systems at the edge of Earth and space. And so here's the edge of space. This is an image taken from orbit. And when we look at it, we can see, well, the limb of the Earth, the stratosphere, the troposphere, the upper atmosphere, and outer space. And what's really remarkable, and I actually brought a little prop. I prepared a little prop because we often don't realize how thin our atmosphere actually is, how incredibly thin it is. So here's what actually is going on, from 0 kilometers to 100 kilometers. This is the Kármán line. But so I marked it off here with blue color, so I'm going to pass it around. So the way you read it is, this is the center of the Earth, that's the surface of the Earth, and that is the atmosphere up to 100 kilometers. Just so you get a sense, this is in the right proportions. So up to about 20 kilometers or so, you're pretty much, the troposphere itself is where most of our weather occurs. What's interesting is the thickness of the troposphere is non-uniform. So the troposphere is actually much shorter at the poles. It's about 9 kilometers, about 17 kilometers at the equator. So the troposphere is non-uniform in terms of its thickness. Of course, we have the famous lapse rate, so the temperature gets colder. But then once you hit the tropopause, temperature is actually almost constant, actually going slightly up again. Throughout the stratosphere until you hit the stratopause, which is the boundary between the stratosphere and the mesosphere, and then temperature starts going down again. And we know that, I like this chart because it shows you, where different vehicles operate. Free jumps, incredibly high, this is really amazing. And of course, what's cool these days is that you can go and take those measurements yourself. So what I'm showing you here on this chart is some, basically a systems problem that we used to do in unified engineering. Unified engineering was our sophomore class in aerospace at MIT, where, 2 or 3 weeks to design a high altitude weather balloon mission with a payload, with a little gondola, with an Arduino, with some sensors. And for literally about $500, you can do this mission. And student teams do it on their own, but I think it's very effective to do it as part of formalized classes as well. So that image was taken. So this is some years ago, 2013. Was taken at the apogee. And how do we know it's the apogee? How do we know that this was taken at apogee on the left side?
Because the balloon popped?
Because the balloon popped, yeah. We want this. We want the balloon to pop. And in fact, we've done, over 30 of these missions. And what you don't want is to underfill the balloon. It goes to altitude and reaches equilibrium. And then it drifts off into the Atlantic Ocean, which has happened to us. You do not want to do that. It needs to go up and pop. And you see in the data exactly what's happening. So temperature, pressure, altitude, and vertical velocity. Those are the four things we're seeing here, measured by essentially an Arduino Uno. And it's very interesting to look at the data. So for example, we started here early in the morning. We usually launch from a mountaintop like Mount Greylock, which is the highest peak in Massachusetts. So you can see we're on the ground here, 0 altitude, and temperature's going up. Do you see that? That's the morning air warming at the point where we're launching. We're launching, and then temperature goes down, as we expect. And then you see temperature is actually settling down at about minus 20 Celsius. When you look at the atmospheric model, you realize, but it should be colder. It should be like minus 50. So one of the big things you learn is that's the temperature that the sensor measures, but it has warmth. It's warmer than it should be because there's heat from the gondola itself. So you're measuring the self-temperature at that point, not the atmospheric temperature. But you see that clearly we've reached the tropopause. And in fact, you see temperature was starting to go up. Then the balloon bursts at 21.6 kilometer altitude, which is just shy of 100,000 feet. And then we start going down very quickly. This chart shows you the vertical velocity. Vertical velocity is almost constant, going up 5 meters per second. And then the balloon pops, and immediately you start dropping like a rock at minus 18 meters per second. And then gradually, the speed of the fall is slowed gradually as the atmosphere gets thicker, and it's this exponential decrease or increase of the density. Another interesting thing you see is after we've landed, you see we're basically landing here, there's still vertical velocity recorded, right? Like an hour later after landing, there's still a vertical velocity recorded. Why is that happening? What is this telling us, this noise?
Earthquake?
Could be. It's not an earthquake.
San Francisco?
Is the payload blowing around somehow?
Yes, Professor. Payload got hung up in a tree. It's hanging in a tree. The accelerometer is still recording, right? The vertical velocity is still being recorded, and it's the wind that's shaking the payload hanging off a tree after it's already landed. So what's my point here? My point is that with relatively inexpensive sensors that you guys can all build, with relatively small budgets, we can get a lot of information these days. And this is just one balloon, one payload. So my topic today really is, what if multiple of these systems collaborate together, work together to fulfill a bigger mission that none of the systems individually can actually satisfy? The prime example for that is perhaps the Coast Guard, right? So this is a very famous program, or shall I say infamous program, called the Deepwater Systems Program. The Coast Guard traditionally, its job is to rescue fishermen that are in trouble, prevent drug smuggling, just maintain control and situational awareness of U.S. territorial waters. So that mission's been getting more and more complex over the years, and the Coast Guard launched a program in the early 2000s called the Deepwater Systems Program, and these are all of the assets that they proposed to develop. It became, it ballooned in cost. It became a $24 billion program, and it was shut down by Congress in 2012 because it was overrunning. And notice the platforms that are here. These are huge ships. These are big, cutters, patrol boats, C-130. There's some drones, but what's missing here? Satellites, right? There's no space assets shown, right? So I think this is a decade ago, roughly. I think today, if we were to reboot a program like this one, we would probably do it differently. We would use smaller assets, maybe we would use commercial data, and we would do data fusion in different ways. And that's really what brings me to the system of systems topic, which is one of our, I think, hot topics in system engineering. Probably the most well-cited paper on system of systems is listed here at the bottom from the System Engineering Journal. And I'm really happy to see Cliff here, Cliff Whitcomb, who's the editor-in-chief of that journal. That paper has gotten over 2,500 citations since it came out in over 20 years ago. What's important is the definition of a system of systems. What is truly a system of systems? There are two characteristics of it that actually would disqualify this traditional Coast Guard architecture. It would actually not be a system of systems because it would fail both of these tests. The first one is operational independence of the components. What does that mean? It means when you essentially, well, we could argue on this first one. Maybe that one it would satisfy. The idea is that if you break the link between the systems and the system of systems, each system individually can still operate. You still get value from it. But it definitely fails the second test, which is managerial independence of the components. Meaning the assets they're all owned by the Coast Guard and kind of centrally managed. In a true system of systems, these assets are not managed, owned by the same entity, by different organizations. Yes?
So I would have called this an enterprise.
Well, yes, there is.
Because it's financed.
This shows you the physical assets. There is an organization, there are financial, there's Congress, absolutely, there's an enterprise. But the actual assets that have sensors on them that are executing the mission in the field, that's typically the system of systems. But so technically, this is not a system of systems because it, at a minimum, fails that second test of managerial independence. So what I want to do now is share with you some work that we do in these system of systems at the boundary of the water, the ocean, air, and space. And specifically look at these four. There's a ton of research questions around system of systems. It's a really interesting field. And what is interesting, though, is because we can build small systems like these weather balloons and get real data, we can now experiment with system of systems even as universities. You don't have to have $1 billion budget to really experiment and get real insights into these questions. So I'm going to look at these four. First one is, how can data that's obtained from different system of systems be combined or fused to create better situational awareness? Since a lot of the value of a system of system is from the heterogeneity of the data that you get. What about operating in domains that typically been very separate, like oceans and space? You saw no space assets on that Coast Guard chart. What about reconfigurability? The ability to change not just the position, but the trajectories of the orbits. Is there value in that? And then finally, this is sort of the, let's go beyond the Earth. How can system of systems help extend humanity's presence beyond Earth's surface? So let's look at the first one. So this is the question of, we have all these different assets operating in a system of system, they all collecting data. How do we fuse that data? How do we credibly combine that data to get to better situational awareness and better decision making? On the left side, you see an analysis that was done by a former student of mine, Veronica Foreman, who's now at SpaceX, who looked at the emergence of the new generation of low Earth orbit satellites and constellations. And it's really dramatic if you look at these charts. So the different color curves show you the different types of satellites, communications, intelligence, those are a lot of the military satellites, and then look at remote sensing. That's this green curve here. Look at that. A lot of that has to do with Planet, the company Planet, having a very large fleet of small sats, but the amount of remote sensing satellites has gone up dramatically. This is 2020. If we added all the Starlink satellites, there's over 2,000 of them now. The blue curve will also rise sharply. So the amount of remote sensing and communication satellites that are in orbit now is absolutely unprecedented. The challenge is that many of them are still operating kind of on their own, or not really coordinated. So you have different Earth observation satellites, UAVs as well. And the big challenge is, what if you observe the same spot on the Earth, but with different sensors, even at the same time? How can we make more sense of that? And so we worked with a company called LabSphere. It's a small company in New Hampshire, but they're world-class in calibration. So most of your iPhones or Samsung phones have cameras in them. Those cameras were almost certainly calibrated, their color calibration, with equipment from LabSphere. One new product that they've developed is shown here. It's essentially an array of mirrors that are placed on the surface of the Earth at certain places that shine sunlight from the mirror into the payload, into the cameras of either a UAV or a satellite. And the value of that is to be able to do what's called vicarious calibration. So that if you're observing the same spot on the Earth, but with very different cameras, you can calibrate against an absolute standard, which is what these stations allow you to do. So the purpose of this project was to understand whether there's value in this kind of cross-calibration from different sensors. And just to show you that this is a real issue, let me hide this here. Here's an example of the same phenomenon on the Earth observed by two different satellites almost at the same time, 16 minutes apart. And credit here goes to Wilfried Schroeder, who's at NOAA. He's really a world expert in wildfire detection using satellite images. So on the left you have an image taken by Landsat 8. And it's a 30-meter ground sample distance. And you can see in red, so it has multiple bands, right? Red, green, blue, near infrared, mid-infrared. And then 16 minutes later, there's a European satellite, Sentinel-2A, flying over the same place and taking an image as well. And you can already see this one is a little darker, right, on the left side. So there's some color differences, just 16 minutes apart. So then what Wilfried did is to overlay the two, because what's important to the firefighters is where exactly is the fire front? How many pockets of fires are there? Where do we deploy? Where do we stay away? And you see the scale here is, this is 4 kilometers, so this is about 2 miles, 2.5 miles. So this is a relatively small area. And you see that both satellites, using the same algorithm for extracting, where the fire is, come up with different answers. You see that they're not right on top of each other. So which one is right? We don't know, because there's no absolute cross-calibration of the two. This could be a big issue. If you're going to send your firefighters here versus here versus here, and you can tell by the way the wind direction, right, where the wind is coming from, this is a real artifact of a system of system using multiple assets with non-cross-calibrated sensors. It's a big issue. So what we did in this project is to develop a model of the value of calibration in remote sensing. And essentially, you start on the left side, you have N sensors. These sensors could be on the same platform, right, on the same UAV, same satellite, or different ones. And you're tasking them to take images in certain bands at certain times, at a certain amount of time. So you have acquired measurements. These are raw measurements. The next step, and there's some error introduced just through the acquisition. The next step is data conversion. So this is where we're correcting the images. So typical correction of satellite images are orthorectification. Right? You're taking the image at a slant range. So it's kind of a skewed image. You have to rectify it and properly also georeference it. Then you have color corrections, calibration factors to correct the colors. As sensors get older, cameras get older on orbit, the red, the green, the blue are changing at different rates. So a 10-year-old camera that's been in orbit for 10 years is not taking the same images as a young camera. So it's pretty involved. That's data conversion. And then what are you seeing in those images? So what I just showed you here, this is called data classification. Which pixel shows you fire and which one is a non-fire pixel? That's data processing. And then finally, actionable information. What do we do with that information? close down the lake because or close down this bay because there's an algae bloom, right? That's a decision. Don't send your firefighters to that coordinate because that's where the fire front is and is moving. And so each step of the way, you have different errors that are introduced from acquisition, data conversion, data processing and classification, and then finally decisions. And so what we're trying to do here is essentially show that by properly managing your system of system at the front end, putting the right sensors in the right place at the right time, and then carefully being aware of all the error accumulation through this data pipeline, you're going to come up with better decisions than if you had no data or if you only had one sensor. Does that make sense? That's basically the idea of this model. And to show you how dramatic this can be, I want to show you this example. This is from Vegetation Analysis. This is a very famous index that any of you work in or with agriculture or vegetation. NDVI is a sort of the bread and butter of the Earth imaging for vegetation analysis. It's essentially an index between 0 and 1 typically, of how much vegetation there is. And basically the way you calculate NDVI is you take your near infrared band, the intensity, and you do this pixel by pixel. The intensity of your near infrared minus the red band divided by the intensity of the near infrared plus the red band. So it's normalized. So if it's class 1, it's below 0, it's negative, meaning it's a bare land. There's no vegetation there. And then, well, this is bare, so there's maybe very little, low vegetation, moderate, and then high vegetation is NDVI class 4. So the image on the left was taken in Colorado from space. It's a space image, 1 meter ground resolution. And then on the right side, you see that same image, but it's now been processed through that NDVI classification into these 5 classes of images. And so the question is, does it really matter whether the colors are right in your images? Is a 1%, 2%, 3% error in the intensity of those bands make a difference or not? And so just to illustrate that to you, that even small errors can have big amplification downstream. I want to show you on the left side, this is the binning of that image that we just saw, right? So NDVI class 1, 2, 3, 4, and 5. And then we introduce into the spectral ratio. So the spectral ratio is the ratio of the near infrared to the red band, an arbitrary error alpha. So alpha is like think of it as a noise level that we can, an error level that we can introduce positive or negative error to the spectral band. And then on the right side, you can see, you know, if there is this much error, you're going to misclassify some of those pixels, right? They should be a class 5. There's a lot of vegetation here, but it's actually not. And so what I want to show you is this point here. So that graph on the left matches this point here. What just shows is a 3% error in the spectral ratio for class 5, which is the high vegetation area, leads to a 60% error in classification of pixels. So that's a 20x amplification of error. A 3% error in calibration of that sensor, of those bands, leads to a 60% error in classification of where the highly vegetated areas are. Right? So it's oh, 3% error, no big deal. It is a big deal once you've gone through this whole pipeline all the way to classification and eventually decision making. And that's the thing about these certainly remote sensing, but system of systems, is that small errors that you think are not a big deal can amplify. And obviously here the amplification is because of the thresholding. Right? Whenever you have thresholding in a system, a small error just puts you over that limit. So we're continuing some work on this. So this is, we haven't actually published this yet, but it's almost ready to submit. Using satellite imagery from different satellites for detecting and mapping solar farms. So this is a lot of solar farms in this country are in California, in the desert. And so this is essentially the process of getting the raw imagery, doing the corrections, extracting the pixels. We also did some ground verification on some of these to find, where is in fact, what's farmland? So this is farmland. A lot of farmland is being converted to solar farms. And then doing the analysis of how much annual capacity does that solar farm actually have. And so by doing things properly with correction factors, we think we can predict solar farm, not just counting panels, but actually saying, oh, it's a panel of that generation and it has 1 gigawatt capacity per year. And of course, we would love to do that globally, right? So that we can see, do the statistics that are published on solar farm deployment actually match what the satellite images are telling us. Because one thing we can probably all agree on is what's the truth these days, right? It's kind of easy to get confused about what's true, what's not true, who's claiming what. Satellite imagery doesn't lie, as long as you process it properly. That's one big power in it. So that's the first question. Yes?
Yes, so in slide number 11, you show that 3% error leads to this 60% reduction.
Yep.
Right, in this classification. So I'm thinking, your classification algorithm, is that designed with some robustness to the error, or so does this lead to improve the classification algorithm, or you try to reduce error? So what?
So this is purely driven by the way that NDVI is defined. The NDVI, these classes of NDVI are pretty standardized. They're used globally around the world. And people publish data on land use and agricultural yields and things like that. So we don't want to change that classification and the thresholds because they're a global standard. The challenge is feeding into that classification to have the proper corrections. And the point I'm trying to make is when you have a complex system of system with multiple different cameras, different platforms observing the same spot on the Earth, and you're not careful about calibrating that information, it can lead you really astray.
Thank you.
Yeah. Okay, so second question. Yes, is there a question there? Yeah.
You mentioned that there's like an unprecedented amount of satellites orbiting around right now, and that obviously has scope for like a lot of opportunity for people down here to like open source that data and use whatever data we can collect. But are there challenges with like proprietary formats that those satellites operate with, and how like the maximum amount of people here can't use that data because they don't have those proprietary formats available to them?
Yeah, great point. So the question is, many different satellites, different formats. Some are private, some are government-owned, some are commercial. How do you? The formats are definitely different. There are some formats emerging as kind of de facto standards. GeoTIFF comes to mind. And then I also highly recommend most people working on this GIS, they're in the global geographic information system field. There's a great open source GIS platform called QGIS. Probably the market leader here is Ezra, which is quite expensive. And I'm sure Cornell has a license as well. But QGIS is open source. And it's really quite good. All right, so next question. What about oceans in space? So here, I'm assuming you've all heard about the project that Professor Haji and I are doing together called Pearl. If you haven't, you're going to hear about it now. So this is a project we've been collaborating on for a couple of years. This is another system of system. This is a project we're doing with the MIT Portugal program. So you see the ocean, and under the ocean there's a lot of stuff. We actually know less about the Earth's ocean than about Mars and the Moon. It's kind of stunning. The fraction of especially the bottom of the ocean that we haven't really explored yet. So we have underwater cables, we have ROVs, which are remotely operated vehicles. They're tethered to a ship. We have AUVs, which are autonomous underwater vehicles. We have gliders. And a lot of these vehicles are kind of operating one at a time. Big challenge is communications underwater, battery, limited endurance through the batteries. And then we have our satellites, which we've already talked up here. So the idea of this is that in a system of systems, there's going to be some platforms that create an interface between these worlds. So Pearl is essentially designed as a platform. It can move, but its fundamental idea is to connect those vehicles under the ocean, like AUVs, with satellites. So the operating idea is that an AUV comes and docks with Pearl, recharges its batteries, offloads its data, sometimes terabytes of data, and then very quickly the AUV can leave and continue its mission. No humans involved, no lifting an AUV with a crane out of the water. That's the vision. And then the AUV is off again. Pearl sits there, solar powered, and recharges its own batteries, solar powered, and then basically sends the data either through a high bandwidth connection like Starlink, 60 megabits per second, or a lower bandwidth connection like Iridium, and to shore, where ideally within minutes, you should be able to get almost real-time data from under the ocean, which is currently not possible. So in the spirit of being able to build and prototype and operate, so this is a little video here of Pearl operating on a pond in Cape Cod. This is, by the way, accelerated. This is about a 4x speed. So you see the design of it, the concept, the design, the implementation, and then a lot of data coming off of Pearl. So the beauty, of course, of this kind of marine systems is that you have easy access to them. As opposed to Professor Peck and I were talking, the space systems, you launch them, and if you can launch one a year or one every other year, you're lucky. So the accessibility of these kinds of systems, being able to troubleshoot them, go back, is really quite positive. But you have a lot of challenges. So that's a view inside the electronics box of Pearl. Lots of sensors, lots of wires, so complexity management becomes a big issue. That's inside the system. The data, we come back to calibration. All this data shown here is just temperature data. But there's 6 different traces. You see the day-night cycle. Some of it is internal temperature. Some of it is external temperature of the air, of the water. And then here is a weather station that's located very close. And so you can compare the kind of absolute standard against what we're seeing here. And you learn a lot very quickly from this. So what does this have to do with system of systems? You saw the satellite links. So this here is an initial analysis that we did on the latency in the system. And the latency is really quite revealing. The way that the data is brought to shore is basically by collecting the data from all the sensors and sampling it, for example, at 1 hertz, batching all the data into CSV files, essentially. And then you have to go through all these steps: formatting, transferring, file compression and encoding of the satellite terminal. Then you have to have a successful handshake, right, between Pearl and the satellite. Then Iridium has inter-satellite links, and that's kind of invisible to us, exactly which satellite it gets routed to. It gets downloaded, and then eventually it arrives at a server, on an FTP server, where the file arrives, and it's time-tagged. So because everything is time-tagged, we can reconstruct the latencies. And what we found is, at least the way we had set up the system, that the Iridium link had about 42 minutes of latency end-to-end. Server to server. Server on Pearl until a shoreside server. And we're still working to figure out exactly how much time is lost where, but you can see the point is it's stochastic. There's a statistical distribution. The red bar is Wi-Fi. If you're really close to shore, you can stream Wi-Fi to the platform, and that's essentially instantaneous. So satellite links are stochastic. And I think that means if you're operating a complex system of systems where you have a mix of RF links, optical links, satellite links, if you're doing underwater, it's going to be sonar, you cannot assume that every link, every handshake is going to be successful and free of latency. So dealing with a reliable system of system with multiple latencies in the system is a big challenge. So under the connecting oceans and space theme. So let me talk to you about reconfigurability. So you see we keep going back up and down between space and the ocean. What about reconfigurability? So one of the projects we're working on right now is with the Aerospace Corporation. Some of you have heard of them. They're a nonprofit FFRDC, really a great organization. And one of the big challenges or opportunities is modularity. So the idea of this mission is we call it ROAMS, Reconfigurable On-Orbit Adaptive Maneuverable Satellites, is to essentially launch into a low Earth orbit, multiple satellites, transfer to a GOM orbit. GOM stands for Global Observation Mode, and I'll show you what that looks like. Calibrate your sensors. Remember, we talked about calibration, very important. And then you have certain targets on Earth, like wildfires, for example, things that are moving, that are dynamic. You want to focus on that target a lot. So you transfer to what's called regional observation mode, which means that you're going to get a lot of observations of that one target at the expense of revisiting the rest of the Earth. And then eventually, when you're done, wildfires typically last a week or two, then you reposition yourself to the global observation mode, and then eventually you deorbit because we do not want to create orbital free. So the challenge is you need propulsion, ideally hybrid propulsion, so you can move fast or slow, and you need modularity in your cameras, your avionics. And so this thing down here on the lower left is essentially a new standard for spacecraft modularity that aerospace has developed called SATCAT-5. It's an Ethernet-based standard. And so we've been testing that, and it's been working really well. So to show you what that looks like, global observation mode looks like this. This is an ISS-like orbit, so it's 450 kilometers at an inclination of 51.6. And so this is a 16-day simulation. So over the course of 16 days, you see the ground tracks. We are pretty much filling in between our upper and lower latitudes. We're filling in most of the Earth. And so you're guaranteed to see your target at least once every 16 days. But by that time, the wildfire is perhaps over, right? So the idea is cleverly choosing our orbit using propulsion, and we don't need a lot of delta V, but exploiting this phenomenon here, which is essentially using the oblateness of the Earth, the J2 effect, to slightly tweak the orbit to bring it into a kind of resonance that's called a repeating ground track. And the key equation is this one here. So this here is essentially the drift rate of the right ascension of the ascending node to essentially tune essentially the drift rate so that the ground track will always be repeating. And you can see here the parameters that we can play with are the inclination. Changing the inclination is very expensive, so we typically don't change the inclination. And then eccentricity and orbital altitude, or semi-major axis A. So by properly tuning the orbit, just slightly tweaking it, we can have a dramatic impact on the revisit times of the satellite. And so this is what it looks like once you're in the regional observation mode. You can see this is the same setup as before. We just slightly changed the altitude. And now the ground track is right on top of each other. So it means if we have a wildfire, for example, here in California, we're going to revisit that much more frequently, at least daily, if not more often. But you have to put your satellite right here in the sweet spot. And so again, we have a situation where a pretty small change can make a big difference in terms of how the satellites behave and how the revisit frequencies are happening. Of course, you need fuel, and so the number of maneuvers you can execute with a small satellite, 6U or 12U, is limited. the faster you want to go, the more fuel you're going to burn. And so one of the ambitions we have for the future is refueling, the ability to refuel our satellites, even small satellites. And so we had a really great opportunity. It came up pretty short last summer to launch a payload on New Shepard 17. So New Shepard is a suborbital vehicle that Blue Origin's been operating. I'm sure many of you have heard about it, but primarily from a human perspective, space tourism. But almost every other flight of New Shepard is payloads, scientific payloads. And just to show you what it looks like, the mission itself is really quite short. It's like a 10-minute mission. And this is the acceleration, the G level. So this period here, you get about 3 minutes of very, very clean microgravity at the top. And so what this experiment was about is showing, can we do fuel transfer? If you notice, you're going to see the fuel transfer. You see these bubbles here? This is what we expect in microgravity, is essentially this fluid behavior as we're transferring from one tank to another. But it is pretty complex. It's a fluid gas mix, essentially. And so one of our conclusions from this experiment was maybe we shouldn't transfer fuel like we pump gasoline into a car. Maybe a better approach in space is to swap cartridges, to basically refuel spacecraft by swapping cartridges instead of trying to transfer fuel across an interface like that in microgravity. But it was a great time, and the students, this is in West Texas, very, very, and a great customer service as well, Blue Origin, the way they process the experiments. We were really impressed by them, and good data as well. So this brings me to the final point, which is, the final question is, how can systems help us not just create better situational awareness of the ocean, the air, and space, but eventually help us expand beyond the Earth? And so this is a somewhat complementary research area that we've been working in over the years that I typically label as space logistics. So what if we went with a mix of human and robotic vehicles, not just resupply the ISS, as you can see here. By the way, this is pretty impressive. The ISS, especially since the shuttle retirement in 2011, has been resupplied from 5 different launch sites on Earth. So obviously you have Kennedy Space Center here, but we're also launching the Cygnus from Wallops. This is Kourou in French Guiana. This is Baikonur in Kazakhstan. And then this is Tanegashima, which is the Japanese launch port. So just resupplying the ISS has been a major challenging operation. Here we have a Mars campaign scenario with robotic precursors. So these 3 are potential human landing sites. And we would send a robotic precursor first to really do detailed analysis of each site and then select the final one. This is very similar to the Artemis program. This is but without the gateway, an outpost at the lunar south pole, and then basically local exploration around that with surface transport. This is my favorite scenario, but you will not find it in any official design reference mission. I call that the nomadic scenario. So the idea is you pick one of the poles and you land there. You do surface transport, but you take everything with you like a caravan, including your ascent stage. And then you go as far as you can before your radiation dosage accumulation, and you run out of supplies. And the crew leaves and comes back to Earth, but leaves everything behind. All the vehicles, everything's left behind. The next crew lands, because we can now do precision landing pretty well, where the old crew left off, and they do the next leg. And you keep doing this until you reach the other pole. That's the nomadic scenario. Personally, I think this would be a lot more exciting than building an outpost and basically returning to the same place over and over again. But again, you will not find this on any official design reference mission at NASA or any other space agency. So the point here is that There's a software that we've developed called Spacenet that allows us to simulate these missions and campaigns using a technique called discrete event simulation. And if you just look at these numbers, so how many nodes are there in the system, how many edges, how many missions, how many mission events. So a mission event would be a landing, a takeoff, a rendezvous, transferring from a propellant from one vehicle to another. Those are all mission events. So you see there's a lot of them. And then the final thing is the element types are the types of vehicles, and then elements are how many instances of vehicles are necessary to execute each of these campaigns. Obviously the Mars campaign is the most complex one. And then these are the durations in Earth days. So some of these this is like a 20-year campaign. And so this is a very, very complex undertaking. And if we learned anything so hundreds of events over thousands of days, this is becoming a system of system, right? No, you can't expect one single agency to operate and own all these vehicles. And you can't also assume that every one of these events, mission events, will be successful. Some of these will fail. And that's why, what we need here is a system of system that has multiple redundancies, multiple different vehicles that collaboratively can achieve this mission, but are mainly owned. Some might be commercial, some might be government owned. And then the other thing I would say, we've learned that we can't bring everything from Earth. If we're really serious about doing this, at some point, we're going to have to learn how to harvest local resources. So our latest project is Orbital Reef. So we joined this team. This is Orbital Blue Origin. You've heard that the ISS is supposed to fly until 2030. I'm starting to have some doubts whether that will actually happen, with the Russians and the political situation currently. So we do need alternatives for humans in space, and this is a commercial station. It's very modular. As you can see, it has a core, and then each of these modules a different customer would come and dock their module. The station would provide life support, basic logistics, obviously attitude control, power, communications. But I have high hopes that this will be a successful project. It's backed obviously by Amazon, and so there's a lot of rigor, and the team is growing very fast. So here's an initial analysis of orbital reef buildup and resupply. So talking 2026 to 2029, and when you look at the modules, the vehicles that are required up here in orbit, you can see that this is also a system of systems. Perhaps you could argue that is there a single managerial entity that owns these? And I would say no, because there will be a consortium here, but the vehicles coming and going are going to be quite heterogeneous. So very exciting, I think, an exciting alternative to how we've been doing things. So my takeaway messages are that when it comes to system of systems at the Earth to space boundary, the amount of systems that are being deployed is rapidly increasing. Definitely satellites, but UAVs, and it's in remote sensing, in telecommunications, intelligence, so ISR. Critical issue is, certainly for remote sensing, is cross-platform calibration. How do we fuse the data from all these disparate sensors, properly calibrate them so that the decisions that are made based on that fused data are the right ones? We saw the delays in the Pearl to Iridium link. So you can't design a system of system deterministically. You have to design it stochastically, because there's random processes happening, like communications delays. Reconfigurability in system of systems means what? It means that it's the ability to tune the system, to change things like locations, trajectories, revisit frequencies, so that the system of systems can respond dynamically to events that are unfolding, like the wildfire that we saw. And then, finally, if we think beyond the Earth, I do believe that as we go beyond the one mission at a time paradigm, system of systems are going to be enablers of interplanetary supply chains that will help us extend human presence beyond the Earth. And just a few words about our lab at MIT. So we have, I think, a very diverse team. In the ESL, the Engineering Systems Lab, my colleagues at Crawley, looking primarily at system architecture. Dan Hastings, who's also our department chair right now, is looking at system engineering. Nancy Levison is focused on safety. And also, I think it's good to look at or have a diverse set of sponsors. I think NASA has been really very steady over the years. Aerospace Corporation, Airbus, Ford, MIT Portugal, we talked about. JWAFS is an interesting program at MIT. It's the Jameel Water and Food Security Program. They're also very interested in remote sensing. And then finally, Blue Origin. So with that, thank you, and really hope for a good discussion. Thank you. Yes, Professor.
So I have a number of questions. A fascinating talk, by the way. Thank you very much. But a number of questions around specifics. A general question, though, is how do you see systems of systems approach like the one that you're describing? How do you see it interacting with other existing systems of systems? So, for example, in the case of space communications, there is, or will be soon, 4G capability in space, LTE protocol. Similarly, there is, and that'll have delay-tolerant networking built in, which would, I guess, address some of the interests specifically of your water-based platform. So, but just generally, can you talk about how one would look at that from a kind of a formalism perspective? How do you acknowledge the capabilities that other systems could bring to this if your goal is to design stochastically?
I think when you look at it as an information network, right, with limited bandwidth, limited power, delay, and you have certain it has to start with the requirements, right? What's the use case? Do you need so for example, in the case of Pearl, and we talked a lot about what's actually our communication requirement. Do we need to be in a system, do we need to be in direct contact, real-time, duplex channel connectivity, high bandwidth at all times? And as soon as you lose the channel, you can't continue the mission. That's the most stringent requirement you would have. So any terrestrial standard like 5G, LTE, you don't want to lose that connectivity. Can you have a duplex link, but it's low bandwidth? Can you have an intermittent link? Can you have really intermittent links and just do kind of like we're doing with the Deep Space Network right now, where we're batching data. We have certain windows of communication that are pre-planned ahead of time, but they can be a day or two apart. Can you operate? So it has to start there, and then the architecture that you choose for your communication has to be a function of those requirements. And redundancy, redundancy. So for Pearl, for example, certainly in coastal areas, there's essentially 4 options for connectivity. There's Wi-Fi when you're close enough to shore. There is the cellular system, which is now switching over to 5G. We have 4G, LTE, 5G. There's Iridium. There's also Starlink. The big problem with Starlink we've had is the terminal is very power hungry. So the Starlink terminal steady state consumes about 100 to 110 watts steady state, which is enormous for a platform like Pearl. We would essentially deplete Pearl's batteries in 2 or 3 hours, I think, if we operated Starlink without interruption, which then brings you back to, okay, I have high bandwidth, but I can't operate continuously at high bandwidth because I don't have enough energy on the vehicle. So I'm not sure if I really answered your question from a formal perspective, but it's very, very coupled, everything.
I guess what reason I'm asking is it seems like some of these resources already exist in a way that's not stochastic. In other words, you could sync up with LunaNet or something like this as a means of communication whether we're talking about Pearl or anything else. So if there's an existing element like that, that could be part of your system, or a system of systems, then that's not really subject to kind of a stochastic analysis. You sort of take it as given, and then how do you think about the architecture when that's the case? You can't control that.
Yeah, I'm not sure that really there are no non-stochastic systems
Okay.
in communications. I would challenge that.
Fair enough.
Even if you're at like 99% reliability of the link, it's still stochastic, right? Okay. Yes?
You mentioned one of the challenges when implementing physical objects in space versus the ocean is physical access to the device. Do you think the implementation of digital twins could alleviate some of that challenge?
Yeah, so digital twin is essentially a virtual replica of your physical system that's very high fidelity, right? And so I'm a big fan of digital twins, digital twin research. But if you're really honest about it, a true digital twin is kind of impossible, because what it means is you would have full state knowledge of the entire system all the time. And you know, I think we'll have partial digital twins. So it definitely helps if you have a high fidelity model of your system and its different subsystems, and you can predict failures ahead of time and update the digital twin. That requires definitely an investment in modeling simulation on the ground. And so to have a digital twin, then the question is, so if we go back to this graph here for a second. So let's take the Lunar Outpost mission. That's 140 elements. So those are individual vehicles, right? Like a rocket stage, or the habitat itself, or a pressurized rover. You need 140 digital twins, right, for each of them. That's a huge challenge, right? That's a huge challenge. And there will come a point where, because digital twins are not free, you have to invest in them, you have to calibrate them, you have to keep them updated. So how much money do we put in? Maybe, you know, instead of doing 140 digital twins, we're just going to add 20 physical systems. Some will fail, but how do we split our investment in more physical assets that are not as well known versus more digital investment in digital twins? That'd be a great research question. I don't know the answer. Do we have any questions on Zoom?
Yes.
Go ahead.
I have a question regarding to what is the convention used here in case if you have a loss of packet? So I understand there is a redundancy of communication and among the subsystems, but say you lost information for a given time. Is it normally like you rely on the previous packet received as the current information, or using the nominal of the current event, just get it going?
So the question was, what is the protocol with respect to loss of packets? So it depends what is your, so if you're using TCP/IP, right? If you're using Wi-Fi, for example, or the TCP/IP standard, then the policy is clear. You're going to wait to receive an acknowledgement that your packet was received at the receiving node, and if packets are missing or corrupted, you're going to resend them. But that is not the case with all these links. So that's a really good point. In a system of system, you may have disparate policies, different communication protocols in different parts of the network. And so, for example, in Pearl, one of the issues that we've been running into is these data files get quite large. If the data file is completely transmitted flawlessly and received on the FTP server side, all is good. But if the link was interrupted during the transfer, what happens then? And so I think we're still learning, right? Do you have to wipe out the file, the partial file that was received on the receiving end, and resend the whole file? Do you splice the file and just resend the delta? So you have to really think carefully about your packet policy. Absolutely. But I think the point that Professor Peck was making, I don't know if I'm paraphrasing, but there's a lot of commercial standards that are very robust and predictable that we used on Earth, and we should leverage robust commercial standards as much as possible, even in space and for these complex system of systems. And I would agree with that. Yes? Keep going.
You mentioned Nancy Levinson. I think she works with Storm or SCPA, right? And her thing is all about incorporating the sort of interaction between humans and the physical object, and from the conceptualization phase of safety. So how are you incorporating that in your research?
So we're not formally applying STAMP or STPA certainly in the Pearl project, but so STAMP STPA is a systems theoretic approach using essentially control theory, the idea of nested control loops, and as a source of uncovering hazards or failure modes that could happen in your system, as opposed to a more classic linear chain of events model for accidents. And so particularly where the stakes are high in terms of human safety, I think it's absolutely true that in the system of systems you're going to have a lot of unexpected failure modes that are either driven by human actions or software actions that are breaking safety constraints in the system. And so I think applying STAMP STPA to a multi-vehicle system of systems situation would be very interesting. Yeah.
All right,
Good.
great. Well, please join me in thanking Professor Weck.
Thank you. Thanks.